I shall now discuss point groups with a single inversion axis. Let us start with the point group 1 bar. So, it is a single one-fold inversion axis. Say for example, the inversion axis is along the z direction and we take a projection, a stereographic projection on the x y plane. Now, if we do that, the location of z will be right at the center of the projection, y will be here and x will be here. Now, if we have a point 1 as shown here, then due to the one-fold inversion axis, it will go 180 degree from here, but at a different level, because as it goes through the central point, the level of the point will be different. So, we will have from point 1 will generate point 2 at a different level. So, number of equivalent points in this case is again 2. Let us talk about the two-fold inversion axis, or rather it does two things. It does rotation as well as inversion, and this is equivalent to a mirror, as we will see readily. Let us suppose that in this case the two-fold inversion axis lies along the z axis. Now, if again just as in the previous case we get a projection on the xy plane, z will come at the center of the projection, y will come over here and x will come over here. So, if point number 1 is a given point, if it were a two-fold rotor, its next position would have been over here. Its next position would have been over here, but it is not a two-fold rotor, but a two-fold inverter. So, what happens after inversion through the center, it comes back to the same position as 1, but now the level will be different. So, you see that due to the operation of a two-fold inverter, we also produce two equivalent points 1 and 2, but at the same place, but at different levels. So, 1 and 2 are their x and y coordinates are the same, but their z's are different. Now, if on the other hand we consider that we have a system where there is simply a mirror plane in the xy plane, then what would have happened? If there were a simple mirror plane in the xy plane, what would have happened? The mirror would have been along this line. So, the mirror on the projection will be along this line, and if you have a given point 1 here, due to the reflection through the mirror, it will produce the point 2 at a different value of z. So, you see that whether it is bar 2 or m, it practically shows the same number of equivalent points. So, as a point group, either you take bar 2 or m, because point groups are such that they are all distinguishable, they will produce distinguishable arrangement of points in space. Now, let us go to the three-fold inverter bar 3 as shown here. Now, such roto-inversion axes are present in hexagonal symmetry. So, we have got the x axis, the y axis and the u axis all in the same plane, and the z axis which is perpendicular to that plane. Now, if we draw a projection in the plane x, y, u, then the projection will look like this. X will be here, y will be at 120 degrees away, and u will be again 120 degrees away, and the threefold roto inverter or the inversion axis will be right at the center. So, now if we have a given point 1 here, if it were a simple threefold rotor, the next position of this point would have been 120 degree away over here, but it is not a simple rotor, it is a rotor inverter. So, from this position it will get inverted through the center to come over the point 2, but remember that 1 and 2 are at two different levels so far as z is concerned, and as a result, if 1 is shown by a closed circle, 2 is shown by an open circle. Now, so in the second rotation, 2 should have gone to the position 6. Due to the second rotation, if it were a simple threefold rotor, 2 should have gone to the position 6, but it is not a simple rotor, it is a rotor inverter. So, it gets inverted through the center and comes over here. So, 2 will produce the point 3, and that will be at a different level compared to the point 2. Then comes the next rotation. So, 3 would have gone to point 1 in the next rotation, but it is a threefold roto inverter. So, after rotation it gets inverted to the center and comes over here at a different level. So, 3 will produce 4 at a different level. Then in the next rotation 4 should have come to 2, but since this is a roto inverter, it gets inverted through the center and comes over 5, and in the final rotation 5 would have gone to the point 3, but will suffer an inversion and come to the point 6 at a different level. So, you see that due to the operation of a threefold roto inverter or threefold inversion axis, we get 6 equivalent points. Out of these 6, 1, 3 and 5 are at the same level so far as z is concerned, and 2, 4 and 6 are at a different level. Now, let us consider the roto inverter bar 4. So, the inverter is taken along the z direction, and as usual when we have the stereographic projection, x will be here, y will be here and z will be over here. So, it is an anti-clockwise rotation that we have assumed all the time. So, if it were a simple 4-fold rotor, then the point 1 should have produced a point 2, and then that should have produced a point 3, and that should have produced a point 4, all at the same level. But because it is not a 4-fold rotor, but a 4-fold roto inverter, things will be somewhat different. For example, during the first rotation of 90 degree, 1 should have gone to this position, but then it will get inverted through the center and come over here. So, 1 instead of producing the point 4 actually produces the point 2, and 1 and 2 are at different levels. So, while 1 is shown by a closed circle, it is an open circle for 2. In the second part of the rotation, 2 should have come to 1, but then it gets inverted to the center and comes to the position 3 at a different level. The next rotation, 3 should have come to 2, but then gets inverted through the center and comes to the point 4. So, you see that the number of equivalent points produced by the point group bar 4 is simply equal to 4, 2 of them at one level the another 2 are at a different level. In a similar way, when we come to the 6-fold roto-inverter or 6-fold rotation inversion axis, what we find again, this kind of symmetry element you get in case of hexagonal system only. So, we have got the x, y and u axis in one plane and then z axis perpendicular to that plane. So, we assume an anti-clockwise rotation for the rotor of the rotor inverter. Now, in the corresponding stereographic projection, again we find the point 1, the given point shown by a closed circle, because of the 6th position of the 6-fold rotor, what it should have gone in the first case, this should have gone to this point, but instead of going there, it will suffer an inversion and come to this. So, the point 1 over here should have gone over there, and then after inversion to the center, it come over here at a different level. Now, then this point 2, after rotation, it should have come over here, as a closed circle, but after inversion, it comes over there, point 3, an open circle. In a similar way, you will find that in this location, you will have the points 1 and 4 at different levels, 3 and 6 here at 2 different levels, 2 and 5 here at 2 different levels. So, number of equivalent points in this case is equal to 6, 3 of them at a particular level and 3 of them at a different level. Now, we can consider point groups which combine a rotation axis and a mirror. So, we will now discuss point groups which combine a rotation axis and a mirror. Say for example, the first one in this group, here we combine a 2-fold rotation axis with one mirror. According to the international system, we should write the symbol as 2m, but we put an extra m, there is a reason for it, which I am going to explain right now. So, let us suppose that we have a 2-fold rotor along the z axis and it is doing an anti-clockwise rotation. These are the x and the y axis. So, this is our stereographic projection. Say the vertical plane is the given mirror, because if we write it as 2m, it means a 2-fold axis with a mirror containing that axis. So, suppose this vertical axis is the given mirror. So, this vertical axis will be this mirror can be presented as this line in the stereographic projection. So, in the stereographic projection, we will have the 2-fold rotor right at the center and the given mirror along this line. So, if you now have a given point 1, due to the existence of the 2-fold rotor, 1 will produce the point 2 at the same level, and since we have a mirror over here, point 2 will get reflected to point 3 and point 1 will get reflected to point 4. So, we find that there are 4 equivalent points produced by combining a 2-fold rotor and a mirror. Now, an interesting thing is the location of the points, the locations of these points are such that 2 and 4 they appear to be produced by a mirror reflection from a mirror along this line. Similarly, the points 3 and 1 they are produced by mirror reflection from a mirror over here. So, this mirror was not the given mirror, but we find that this mirror is produced due to the operation of the point group 2m, and if you try to locate that mirror, it will be this mirror over here. So, you see although the point group is 2m, it automatically produces another mirror containing the two-fold axis. So, we write it as 2m. Now, let us go to the next point group. We combine a four-fold rotor with a mirror containing it. Say we have the four-fold rotor along the z direction, and let us have this vertical mirror. We combine the four-fold rotor with this vertical mirror. So, in the projection, the four-fold rotor will come right at the center, and the given vertical mirror will be this one. The given vertical mirror will be given by this line. So, if you have a given point 1, because of the operation of this four-fold rotor, what will happen? 1 will produce 2, 2 will produce 3, 3 will produce 4, 4 will produce 1, like that. So, you see that from one point we produce another 3. So, there are 4 equivalent points. Now, this is a given mirror. So, what will happen? 1 by reflection will produce 5, 3 by reflection will produce 7, 2 by reflection will produce 8, and 4 by reflection should produce 6. So, you see that we produce 4 extra points because of the presence of the mirror. So, total number of equivalent points will be 8 in this case. Now, look at this particular line. So, all the points are arranged in such a fashion as if there is a mirror along this line too. For example, if there is a mirror along this line, then 3 and 5 are mirror reflections, 7 and 1 are mirror reflections, 2 and 6 are mirror reflections, 4 and 8 are mirror reflections. So, although we have not consciously invoked the second mirror, it automatically comes into operation due to the action of the point group 4m. So, that is the reason why we provide for the second mirror in the notation itself. We call it 4mm, and here this is the mirror which really comes into existence due to the operation of the four-fold rotor and the mirror containing it. Now, let us come to another point group written as 2 by m. Here the mirror does not contain the rotation axis. The mirror is perpendicular to the rotation axis. So, again in the x, y, z coordinate system, we assume that there is a two-fold rotor along the z direction rotating in the anti-clockwise manner, and we have a mirror right over there perpendicular to the two-fold axis. So, in the corresponding projection, our two-fold rotor will be right at the center, and where will be the mirror? The mirror will be shown by the periphery of this circle. So, the mirror will be along here. So, if now we have a point given point 1, then due to the presence of the two-fold rotor, 1 will produce the point 2 at the same level, but then because we have a mirror over here on the plane of the figure, 2 will be reflected through the mirror to produce 3 at a different level, and 1 will be reflected at a different level to produce 0.4. So, the total number of equivalent points in this case is again 4, 2 at one level, 2 at a different level. In a similar manner, if we talk about the point group denoted by 6 by m, here we have a 6-fold rotor along the z axis and a mirror perpendicular to that, as is possible in a hexagonal system. Now, if we look at the corresponding projection, the point 1, because the 6-fold rotor position is here, the point 1 would have produced the point 2, point 3, point 4, point 5 and point 6 all at the same level, and since the mirror is lying along the periphery of the projection, 1 will be reflected to the point 7, 2 will give a reflection at point 8, 3 will give a reflection at point 9, 4 will give a reflection point 10, 5 will give a reflected point 11, 6 will give a reflected point at 12. So, the first 6 are in the same level and the other 6 are at a different level. So, the total number of equivalent points in this case will be 12. Now, we would like to discuss point groups which combine only rotation axis. So, this is a case where we have a point group which is denoted as 2, 2 and 2. So, here we combine 3 two-fold rotation axes, one along the z direction, one along the y direction, one along the x direction. So, if we have the corresponding projection here, so one the major two-fold axis, the principal two-fold axis will come at the center, then one along y will be over here, one along x will be over here. So, if we have a point 1, due to the action of this two-fold rotor at the center, it will produce a point 2 at the same level. Now, because of this rotor here, what will happen? This rotor will produce another point from 1 at this position at a different level. Not only that, it will also produce another point from the 2 at 4 at a different level. Now, what about the action of this rotor? By the action of this rotor, nothing changes, number of equivalent points do not change, because if it is a two-fold rotor, automatically 1 should produce 4, 2 should produce 3. So, that the number of equivalent points in this point group is 4. Now, we come to a complicated case, the point group given by denoted by 4, 3, 2. As the name implies, here we combine 4-fold rotors with 3-fold rotors and 2-fold rotors. Now, if we try to figure out in what way the combination can be done, then we will see that the locations of the 4-fold, 3-fold and 2-fold rotors will be the corresponding to the locations of the 1 0 0, 1 1 0 and 1 1 poles, as we find in the stereographic projection of a cubic system. I will explain it here. Now, when we plot the poles of the 1 0 0 planes, the 1 1 0 type planes and the 1 1 1 type planes, we know that the 1 0 0 planes, their poles come over here. So, this is the location of a 1 0 0 type of pole, this is the location of another 1 0 0 type of pole, this is the location of another 1 0 0 type of pole, this is another 1 0 0 type of pole, this is another 1 0 0 type of pole. So, these are the positions of the 1 0 0 type of poles. Now, where do the 1 1 0 type poles lie? If you will remember, the 1 1 0 type poles lie over here. This is one position, then this is another position, this is the third position, and this is the fourth position here. In addition, this is another, this is another, this is another, this is another. So, all the cross marked points, they are actually the locations for 1 1 0 type poles. And what about the 1 1 1 type poles? We found out the 1 1 1 type poles appear in these 4 points. So, these are the locations of the 1 1 1 type of poles. So, these are the locations of the 1 1 1 type of poles. Now, it can be shown mathematically that if you want to combine 3 rotation axes 4 3 2 to form a point group, then they are situated in this manner. That means, if we draw a stereographic projection, in that case, if all the 4-fold rotors lie in this position, if all the 4-fold rotors will lie in this positions, then all the threefold rotors will lie at this position, and all the 2-fold rotors will lie in these positions. So, the 2-fold rotors will lie at the positions of the 1 1 0 type of poles. So, these are the positions of the 1 1 0 type of poles. Right. So, you see that when you combine 3 rotation axes 4, 3 and 2, that means you are combining 4-fold rotors, 3-fold rotors and 2-fold rotors to give you a distinct point group, then mathematically it can be shown that the relative locations of the 4-fold rotors will be lying here. So, this is where the locations of the 4-fold rotors will lie, and the 2-fold rotors will lie at positions shown over there, and the 3-fold rotors will lie in positions given in that particular projection. So, this is what you can see over here, and in such a situation, if you have a point, say given point here, then it will be subjected to the operation of all the 4-fold, 3-fold and 2-fold rotors which exist here in this point group, and as a result we will have a total number of 24 equivalent points produced, 6 around here, another 6 around here, another 6 around here another 6 around here. Out of 24, 12 are at one level, the other 12 are at a different level. In this way, we can describe the point groups, all the 32 point groups, and also can find out what should be the number of equivalent points in every case. So, I have just illustrated a few, and now I would start with what is known as the space groups. So, now I will start with what is known as the space groups. Well, if we know the space group of a crystal, then we can figure out the arrangement of atoms over a three-dimensional crystal, just as by knowing the point group, we know the arrangement of atoms around a lattice point. You see, there have been cases where two identical looking crystals have been found to have different properties. You know, their point groups are the same, but they have different property. Now, the reason later on was found out as due to the fact that although the point groups of the two substances are different, the space groups are although the point groups are the same, the space groups are different. The space group represent the arrangement of points in the, or rather the group of atoms, arrangement of the group of atoms over an extended three-dimensional crystal. Now, it will be quite apparent, you know, what we mean by that very soon. You see, up till now we have been discussing about some symmetry elements like the plane of symmetry or mirror, rotation symmetry or the axis of symmetry, then roto-inversion or roto-reflected symmetry like that, and an inversion. Now, in addition to these four, we find that if we assume that some other symmetry elements can also be invoked to explain the location of atoms throughout the extended three-dimensional crystal, we find things become much more easy. For example, in addition to the four symmetry elements which we talked about in case of point groups, we invoke two more imaginary symmetry elements. One is called a glide plane, the other is known as the screw axis. Now, let us start with a screw axis first. What is meant by a screw axis? Say if we have a simple two-fold rotor along this vertical line, this is a simple two-fold rotor. Now, if 1, 2 and 3 are three lattice points present, then if we have a point A over here, because you know this is the lattice point having a two-fold axis, so A will produce the point B due to the operation of the two-fold axis, two-fold rotation axis at the point A. Similarly, at the point 1, at the point 2, what will happen? If we have another atom attached to the point over here, the lattice point here, then due to the operation of the two-fold rotor, A will again produce a point B at 180 degree. Now, if we go to the lattice point 3, again if there is a given point A, due to the action of the two-fold rotor through this point, we will produce another point B. Okay. So, this is how a two-fold rotor operates. Now, when we talk about a screw axis, it has two functions to play. That means, there are two operations take place simultaneously. One is rotation like an ordinary rotor, and then a translation, along the rotor. So, a screw axis is a symmetry element which does two functions. It rotates like a simple rotor, and it also translates along it. Now, let us see what it means. Say for example, here instead of a two-fold rotor, we have got a two-fold screw axis. So, this is a symmetry element which is different from a simple two-fold rotor. Now, if we have the three lattice points 1, 2 and 3 as before, and if you have this atom A attached to this lattice point, then if the whole thing were a two-fold rotor, then the next position of the point A would have been B prime. But here we do not have a simple two-fold rotor. This sign indicates that it is a screw axis, and in this particular case, suppose the amount of translation is half the lattice parameter. So, the point A, due to the two-fold screw axis, cannot go to point B dash, which it would have done if it were a simple two-fold rotor, but instead it translates half the lattice parameter and goes to B. So, you see that due to the operation of the two-fold screw axis along this line, a point A or an atom A attached to the lattice point 1 will produce the atom B or the point B over here. Similarly, a point A attached to the lattice point 2 will produce a point over here, and a point A attached to the lattice point 3 will produce the next point over here. So, you see that there is a subtle difference in the position of the points or the position of the atoms in case of the two-fold rotor and the two-fold screw axis. So, if we have got two substances which have one a two-fold rotor and another case a two-fold screw axis, the arrangement of atoms will be quite different. For example, in case of a two-fold rotor, if these are A, B and AB, these are the locations of the atoms in space. In case of a two-fold screw axis, the atoms will be here A and B, A and B, A and B. So, you see that the locations are completely different. Similarly, if we have a three-fold rotor, say the rotor operates along this direction, and here you have a three-fold rotor. Now, say 1, 2 and 3, these are the three lattice points along this line. So, if we have a point A attached to this, then A will produce a second point B over here and a third point C over there. Similarly, at lattice point 2 also A will produce B and will produce 3. Remember, the angle between the locations of A, B and C are at 120 degree apart. So, this is what will happen in case of all the three lattice points. Now, if instead we have got a three-fold screw axis, then what will happen? A screw axis rotates and at the same time translates along it. Let us suppose that we have got a three-fold screw axis with a pitch 1/3. That means, the amount of translation is 1/3 the lattice parameter. Then what would have happened? here again these are the locations of point 1, 2 and 3. So, A would have produced the point B over here, but since it is no longer a threefold rotor, it is a threefold screw axis. So, A instead of producing B here will move 1/3 the lattice distance and come over here. Okay? And this again will not produce a corresponding point over here. It moves 1/3 the lattice parameter and produce a point here. Okay? In a similar manner, A will not produce a B here, but it will move 1/3 over there, and the B will not produce a C over here, it will move 1/3 and produce it there. So, you see that in this manner the locations of the points or atoms in case of a threefold screw axis and a threefold rotor are quite different. So, there will be subtle differences in the location of atoms in two crystals having say a threefold rotor in one case and a threefold screw axis in the other case. Now, if we join the points produced by a threefold screw axis one after the other, you will find that they look like a screw kind of a thing. So, and that is the reason why these axes are known as these rotors are known as the screw axis. Now, normally when we have a pure say two-fold rotation axis, we denote it as an arrow. A two-fold screw axis will be denoted as half an arrow. Now, let us talk about what is known as a glide plane. So, a glide plane is a symmetry element which does two things. A normal mirror, it does reflection only. A normal mirror does reflection only, but a glide plane is one which does both the functions, reflection as well as translation along the plane. So, a normal mirror plane does reflection only, but a glide plane produces both reflection and translation along the plane. So, here I am showing a glide plane, so to say. Suppose this is a glide plane in a crystal. These are the lattice points B, C, D, A, these are the lattice points. So, if it were a simple mirror, if the hatched plane, if it were a simple mirror, then the point P would have produced a second point Q dashed over here. But if it is not a simple mirror, but a glide plane, what happens? Then the point P translates along this line on the plane and then gets reflected over here. So, there are two functions, a translation as well as a reflection. So, this is the function of a glide plane. So, we invoke these two types of symmetry elements in order to find out how atoms or groups of atoms will be arranged in a three-dimensional crystal. There, as we already saw, that in case of the location of atoms around a lattice point simply can be found out by knowing the collection of symmetry elements at that point. In case of the distribution of atoms or groups of atoms over an extended crystal, we find that we have to invoke, in addition to the four symmetry elements already we talked about in connection to the point group, another two known as the glide plane and screw axis, and then we have to make combinations of these 6 different types of symmetry elements to yield some distinguishable arrangement of points or atoms, and those are known as the space groups. Just as we could combine the 4 symmetry elements connected with the point group in 32 different ways. Similarly, these 4 plus these 2, the 6 symmetry elements we can combine in 230 different ways. So, just as we have 32 point groups, we have a total of 230 space groups. Just as we have 32 point groups, we have 230 space groups. So, I am now going to describe a few of those space groups. You see, depending on the amount of translation that is taking place along a glide plane, they are given different symbols, so to say. Say for example, if the amount of translation is half the lattice parameter along A, we call it simply small a. Half the lattice parameter along B, we call it simple b. Half the lattice parameter along C, we call it C. And then if it is A0 plus B0 by 2, that means half of the the parameters A plus B, or half the parameters B plus C, or half the parameters C plus A, those are denoted as the number as n, as the letter n. And if it is 1/4 of A0 plus B0 or B0 plus C0, C0 plus A0, this amount of translation, then those glide planes will be known as Ds. So, these are the notations for the different types of glide planes where the translations differ one from the other. Now, in order to denote the space group, the first thing that we have to do is to know the underlying Bravais lattice. Say for example, if we have a primitive cubic unit cell, it is denoted as capital P, then completely face centered cubic unit cell is denoted as F, body centered cubic unit cell is denoted as I. Now, 100 face centered cubic unit cell is known as capital A, 010 face centered cubic unit cell is known as B, then 001 face centered cubic unit cell is known as C, rhomboedral unit cell is given the notation R, and triply primitive hexagonal unit cell is noted as H. So, this will give us the underlying Bravais lattice for a system, for a crystal. So, this is the first thing to remember. So, when we denote, there are two ways again by which we can name a space group. Just as we remember we could denote a space group in two ways, namely, so a point group could be denoted by the Schoenflies notation or the Harman-Ogwin or international notation. Now, say for example, this is a simple space group where we have the underlying point group is a fourfold rotor and a mirror perpendicular to that. That means, when it comes to knowing the arrangement of the atoms at any lattice point, that will be given by the notation 4 by m. So, in this particular case, the underlying point group can be described as, according to the international notation, 4 by m. So, at each lattice point here, we can assume that as if there is a four-fold rotor acting with a mirror perpendicular to that. So, that will give us an idea about the distribution of atoms around the lattice points. Now, when we talk about the Schoenflies notation, this one can be written as C 1 and then it comes to 4H. 4H stands for four-fold rotor and a horizontal mirror. So, the Schoenflies notation tells us that this is the first space group based on the C4H point group. But really speaking, the international symbol is much more explicit. So, what the same thing as C14H in the Schoenflies notation can be expressed as P4 by M in the Harman-Markov or international notation. So, in this notation what we do, first of all write down the underlying Bravais lattice. So, it is a primitive lattice. So, we write capital P and then we write down what are the symmetry elements involved. There is a four-fold symmetry and it will be a mirror is perpendicular to the four-fold symmetry. So, the first part is the Schoenflies notation here and the second part is the Harman-Markov or the international notation. Now, we will talk about another space group. When it comes to the Schoenflies notation, it is denoted as D2H16. That means the 16th space group based on the point group D2H. But as I said already, that it is always better to write down the international symbol which is much more explicit and which can immediately give us the all the symmetry elements that are involved in the space group. So, in this particular case again we have an underlying primitive lattice as we can see here from the unit cell, and there are three mirrors of there are actually one mirror and two glide planes involved here. Say for example, if you have a mirror along this as shown, and there will be say another glide plane perpendicular to that and a third glide plane given by this. So, there are two glide planes, one is perpendicular to x, another is perpendicular to z, and then a third one is a mirror plane perpendicular to y. So, if these are the elements involved over here, then the space group can be written as the primitive lattice P, then N stands for an N type glide plane, M stands for a mirror and A stands for a type glide plane. We have already seen that glide planes can be denoted in different ways. An N type glide plane is having translation of this type, a type glide plane has translation of this type, etc., etc. So, once we write this space group as PNMA, that says explicitly what are the symmetry elements involved in this process.